To understand radioactivity and radiation, we must first examine the types of forces in the atomic nucleus. Gravitational force is the force of attraction between objects with mass. The amount of gravitational force is contingent on their mass and the distance between them. For subatomic particles, this force is present, but not the major force holding the nucleus together. Electromagnetic force refers to the repulsion and attraction forces between particles. These are the forces that hold the electrons around the nucleus. This is the force that holds the atomic nucleus together. This force counteracts the electromagnetic forces. Remember in lecture 1 I told you to pay close attention to the role of neutrons in the nucleus? This is it. The presence of neutrons helps hold the nucleus together. Weak force plays a key role in the possible change of subatomic particles. For example, a neutron can change into a proton and an electron. I know what you're thinking. WTF? Well, this is the force responsible for radioactive decay. Radioactive decay is a process by which the nucleus of a radioactive or unstable atom releases nuclear radiation. In large nuclei, far apart neutrons are less effective in holding a nucleus together. This makes the nucleus unstable and radioactive. Radioactivity results from radioactive decay, which is the process whereby unstable nuclei transform and emit radiation. This phenom has existed longer than we have existed. Unstable atomic nuclei have an imbalance of neutrons and protons, and most importantly, they're radioactive. Most radiation we encounter is natural background radiation that originates in Earth and space. Cosmic rays, for example, are from the sun and stars. However, cosmic rays are more intense at higher altitudes. There are two types of cosmic rays: high energy particles and high energy electromagnetic radiation, or gamma rays. They affect us indirectly by transforming nitrogen atoms in the air to radioactive carbon 14, which ends up in the plants we consume. Now click on the link and watch this very informative video on cosmic rays. Half-life is the time required for the original quantity to divide in half. It can be calculated at any moment by measuring the rate of decay of a known quantity using a radiation detector. It's important to note that half-life is constant and independent of any physical or chemical change the atom may undergo. On this slide, I want you to review the two major methods for radiometric dating. Transmutation is the changing of one chemical element to another. There's both artificial and natural transmutation. Synthetic elements have been produced from atomic numbers 93 to 115, all with short half-lives. Familiarize yourself with Rutherford's example of transmutation. An alpha particle is a common type of radiation. It consists of two protons and two neutrons. It loses energy quickly during interaction. It can be stopped easily by a few pieces of paper due to its large mass and a double positive charge. It does not normally penetrate lightweight material like paper and clothing. It causes significant damage to the surface of a material due to great kinetic energy. It picks up electrons and becomes harmless helium when traveling through the air. And it is deflected in the presence of a magnetic or electric field. A beta particle is an ejected electron from a neutron. It has both a smaller mass and electric charge than an alpha particle and moves faster. It loses energy at a slower rate in air and travels further before stopping. It can be stopped by several sheets of aluminum foil. It penetrates deeply into the skin. Once stopped, it becomes an ordinary electron. It's deflected in the opposite direction to an alpha particle in the presence of a magnetic and electric field. Gamma rays are emitted when a nucleus in an excited state moves to a lower energy state. They are more harmful than alpha and beta particles. They are most penetrating because they have no mass or charge. They are pure energy, greater per photon than invisible and ultraviolet light and X rays. They are unaffected by the magnetic and electric fields and therefore interact via direct hit with an atom. They are high frequency electromagnetic radiation. A little thought question: why do you think Spike Lee named the gamma rays? This type of radiation is covered in your textbook in chapter 13.5. I would recommend reading this entire section. In nuclear fission, a neutron hits a uranium 235 nucleus, which causes it to stretch and fly apart. Energy released is in the form of kinetic energy or fission fragments that fly apart from one another, with some energy given to ejected neutrons and the remainder given to gamma radiation. The result is a chain reaction, or a self-sustaining reaction in which the products of one reaction event stimulate further reaction events. This is contingent upon the critical mass, which is the minimum mass of fissionable material in a reactor or nuclear bomb that will sustain a chain reaction. At or above critical mass in a large quantity of atoms, an enormous explosion can occur, like the nuclear reactor explosion in Japan back in 2011. Please review Albert Einstein's equation E equals mc squared, which is the key to understanding why and how energy is released in nuclear reactions. Nuclear fusion is another section in your book that I would read completely. Nuclear fusion is the combination of nuclei of lighter atoms to form heavier nuclei with the release of a lot of energy. Nuclear fusion is produced by high temperature, resulting in more tightly bound nuclei. Nuclear fusion has the potential to produce a lot of sustained energy for the world. However, a solution is still being sought for reactions to occur under controlled conditions to provide an enormous amount of sustained energy.